Great. So welcome back from lunch. Our second talk for the day is going to be by Ikshu Neithalath from UCLA. And the title of his talk is Skein Lasagna Modules for Two-Handle Bodies.
Thank you, Peter, for that introduction. And thank you very much to all the organizers of this conference for inviting me to give this talk here. And thanks, everyone, for coming to listen to my talk. Okay, so today I'll be talking about Skein Lasagna modules, which are a certain invariant of links in the boundary of four manifolds. In fact, it's the invariant that was just discussed by Paul Wedrich in the previous talk. And today we'll be focusing on the case of two-handle bodies, which are a certain class of four manifolds. All right, so everything I'm going to say in this talk is based on joint work with Ciprian and Monilescu. So yeah, let's get into it. All right, so the basic invariant that we're going to be discussing today is this Morrison-Walker-Wedrich invariant. And today I'm in the very convenient situation of giving this talk right after Paul already talked about this. So in theory, I can maybe skip some of this background material or go through it a little bit quickly, but I'll try my best to still say everything. And yeah, just in case, maybe you missed Paul's talk, you haven't gotten around to watching the recording yet. I know a lot of us are on different time zones, so it's hard to make all the different talks. So I will be going through some of the things that Paul already talked about, maybe a little bit quickly though. So definitely stop me if I'm kind of going through something too quickly or glossing over some details. All right, so just to remind you, what is this Morrison-Walker-Wedrich invariant? Well, it's something that we associate to a framed link in the boundary of any smooth-oriented four-manifold, and it takes the form of a triply graded abelian group, which I'll denote S upper N, and the subscripts here are the three gradings star, I, and J. Okay, so what's the idea behind this is that it's supposed to be a generalization of Khovanov-Rozansky GLN link homology. So I think hopefully we've had enough talks about Khovanov-Rozansky homology that I don't need to remind you exactly what this is. But yeah, just notice that we are using the GLN version. Maybe you're more familiar with the SLN version. And I think hopefully Paul gave you some good reasons in his talk why we might want to use this GLN version. And so here, capital N will always denote, as in like the superscript N here, will denote the theory that we're using, the GLN. All right, great. So now what are these three gradings on our group? Well, the first grading, the star, is what's called the blob degree, because it comes from the machinery of blob homology, which is this kind of a categorical machinery that produces sort of higher derived invariants from more basic ones. It's a bit like factorization homology, if you're familiar with that. But we're actually not going to worry about that at all in this talk. We're only going to focus on the case when this blob degree is 0, and that's when this group has some rather simple topological description in terms of certain diagrams in your four manifold. And the other two gradings, I and J, are the homological and quantum degrees. Those are just the same degrees that you're hopefully familiar with from Khovanov-Rozansky homology. All right, and how is this a generalization of Khovanov-Rozansky homology? Well, as Paul mentioned, what you do is if you just plug in the four ball for your four manifold, so this link L is just a link in the three sphere, then this invariant will precisely recover the Khovanov-Rozansky GLN link homology of the link. All right, great. So now, before I state the main theorem that I want to talk about today, let me just give you a brief description of the two main objects that appear in the theorem. And I'll just give kind of a slogan definition of them at first, and we'll come back and try to define them more precisely. The first main object is the Skein Lasagna module, which is just that Morrison-Walker-Wedrich invariant, but only in blob degree 0. So I've kind of suppressed the other two gradings here. I'm not writing those. The 0 refers to the blob degree. All right. And so if you remember exactly what this is from Paul's talk, great. But let me just give kind of a slogan definition of it for now. Roughly what this group is it's some free abelian group that's generated by all embedded surfaces, smoothly embedded surfaces in your four manifold. But then we're going to mod out by some local relations that treat parts of these surfaces as Cobordism maps in Khovanov-Rozansky homology. So hopefully that kind of explains why we're using the word skein here. It's very much an analogy to the skein module of a three manifold in which you have embedded one manifolds modulo some local algebraic relations. Okay, but still somehow this is a very abstract object. It's something generated by all these embedded surfaces, and yeah, then we mod out by some relations. So it's not a very concrete thing. The other object that will appear in the main theorem is a new thing that we define in our paper called the cabled Khovanov-Rozansky homology. It's a group that we assign to any framed link in the 3-sphere. So for the purposes of this talk, K is usually going to be a link in the 3-sphere, a framed link in S3, and this L will generally be a link in the boundary of some arbitrary 4 manifold. So they're kind of different things. Okay. And roughly, what is this cabled Khovanov-Rozansky homology? Well, what we do is we take a bunch of cables on our framed link, okay, some infinite family of cables on the link, and we take the Khovanov-Rozansky homology groups of all of those various cables and take the direct sum of all those groups, okay? So a direct sum of this infinite family of groups. And then we're gonna use certain specific Cobordisms between these cables, and those give us certain maps on the Khovanov-Rozansky homology, and we'll use those maps to define some relations in this group, and we'll mod out by those relations. Okay, so somehow this group is a little bit more concrete than the first object, in the sense that it's something constructed out of Khovanov-Rozansky homology groups, which are, well, you know, in some sense combinatorial or, you know, more algebraically constructed. They're things you can really get your hands on. That's not to say it's extremely computable or anything. For example, computing the cabled Khovanov-Rozansky homology would require computing the Khovanov-Rozansky homologies of some infinite family of links. And in general, that's very difficult, and in most cases impossible to do with our current technology. So yeah, it's still a little bit difficult to get your hands on, but somehow a bit more concrete than the first thing. So in our main theorem, we're going to relate these two objects. Okay, so now I have almost enough to state the main theorem. But first, I just need to remind you what is a two-handled body. So given a framed link in the 3-sphere, we can form a 4-manifold associated to this by taking the 4-ball and gluing some 2 handles along that framed link. And that's what I'll call a two-handled body associated to that link. The second ingredient that I need before I can state the theorem is a slight refinement of our Skein Lasagna module invariant. And Paul also, I think, discussed this in his talk, that there is a grading on this, not just unrelated to the homological and quantum gradings that appear from Khovanov-Rozansky homology. There's also a grading by relative second homology classes in the 4-manifold. Okay, so when I write this third parameter alpha here in the group, what this means is the Skein Lasagna module, but where I only consider embedded surfaces whose fundamental class is equal to this class alpha in the second homology relative to boundary. Right, remember, the Skein Lasagna module is something generated by embedded surfaces. So depending on the fundamental class of that embedded surface, we get this direct sum decomposition. Okay, so that's what this third parameter here means. Great, so now we have enough to state the main theorem, which is the following. So let's say we have a two-handle body associated to some framed link. In that situation, we have an isomorphism between the Skein Lasagna module of the two-handle body, and this is the Skein Lasagna module with just the empty link in the boundary, an isomorphism from that to the cabled Khovanov-Rozansky homology of that framed link. Okay, so this is the theorem I want to discuss today. So now what I'd like to do is give a couple of corollaries or some calculations we can do using this theorem, then state a few other kind of side theorems that appear in our paper. After that, we'll go back and more carefully define both of these objects, the Skein Lasagna module, which hopefully you're a little bit familiar with already from Paul's talk, and then also the cabled Khovanov-Rozansky homology, which is this new object. And once we've defined those more carefully, then I'll try to give a proof or a sketch of a proof of the theorem. All right, any questions so far?
Well, maybe just the obvious. I mean, presumably this isomorphism is like just not just abstract, not just abstractly isomorphic, but somehow geometrically meaningful. Or I mean, is it like we're just saying two vector spaces have the same dimension, or is it more than that?
A priori, yes. I mean, when I explain the proof, you'll see how the geometry, I think it will once the proof is somewhat explained, it might become a little bit more meaningful in your mind. But yeah, I think as far as applications are concerned, like if all this we're really saying we're just some equality of dimensions of vector spaces, I think that's already kind of a lot of the content of what this theorem is really saying. Yeah. Okay.
Okay, thanks.
Yeah. Okay. So let me just give some calculations that we can do with this. So what I want to do is I want to compute the Skein Lasagna module of some 4 manifolds, let's say some 2 handle bodies, using this theorem. And to do that, I'm going to have to compute the cabled Khovanov-Rozansky homology of the link that it comes from, which, well, I haven't told you exactly what this is, but roughly that means I'm going to have to compute the Khovanov-Rozansky homologies of kind of an infinite family of cables on that link. So let's try it for the simplest possible framed links. So the simplest one is if K is the 0 framed unknot. Then the associated 2 handle body is just S2 times D2. And now to compute the Skein Lasagna module using that theorem, I have to compute the Khovanov-Rozansky homologies of cables on the 0 framed unknot. Well, those are just unlinked, so that's totally trivial to compute. And I'm also going to have to compute some Cobordisms between these unlinks. And it turns out the Cobordisms that we're going to be using are just simple pair of pants type Cobordisms. So the maps are also completely trivial to understand. So in this particular case, we can explicitly compute the ranks of the Skein Lasagna module. And I've written the ranks as a kind of a generating function here. And yeah, we have an explicit formula for what that would be. The next simplest case is if you take the P-framed unknot. And now already things are going to get a bit more complicated. In this case, what we get for the 4 manifold is a disk bundle over the sphere with Euler number P. And now if I want to use the theorem, we're going to have to compute the Khovanov-Rozansky homologies of cables on the P-framed unknot. Well, those are torus links. And in general, it's not really known how to compute or how to write down some explicit formula for the Khovanov-Rozansky homologies of some infinite family of torus links. But in some very special cases, this can be done. So let's now focus on the case when capital N is equal to 2. In other words, that's just the case of the GL2 theory, the case of Khovanov homology, the original Khovanov homology theory. Let's set this parameter alpha, which corresponds to the homology classes of the surfaces that we're considering, equal to 0. So I guess we're only considering null homologous surfaces, which, and remember, the surfaces can be in some sense disjoint. So it's not like we can have surfaces with interesting homology classes as long as they come in pairs that cancel, for example. So it's not a huge condition or a huge restrictive condition. And let's also just focus on homological degree 0 in this group. In that very particular case, the relevant Khovanov homology groups have been computed, and we can use those calculations from the literature to compute the Skein Lasagna modules. And interestingly, it splits into 2 cases, depending on the sign of this Euler number P. If P is positive, the group is identically 0. Well, at least this is only in homological degree 0. That's the only place I can say anything. But in that degree, for all quantum degrees, it's equal to 0. If this Euler number were negative, if the framing is negative, then it's actually rank 1 in quantum degree 0 and 0 in the other quantum degrees. So they're different. And this is going to be a little kind of interesting. On the next slide, I'll explain why this difference is somewhat interesting. And I should also mention how we're able to do these calculations. How are people able to compute these relevant Khovanov homology groups? Well, this is due to work of Pristichki, Stosic, and Rozansky have all, and others have contributed to computing the Khovanov homology of torus links. And the way roughly it works is that the Khovanov homology of torus links is related to the Hochschild homology of a certain algebra, Khovanov's arc algebra. And in particular, in homological degree 0, the group is just the Hochschild cohomology in degree 0 of this algebra. In other words, the center of the algebra. And that's something that's been computed. If you want to extend those types of calculations to other homological degrees, it would involve computing the higher Hochschild homology or higher Hochschild cohomologies of that algebra. And as far as I know, that's not something that's really been well studied in the literature. Okay, so that's how we can apply those calculations to compute things about the Skein Lasagna module. All right, so those are the kind of the main calculations that we're able to do, sort of in some sense explicitly. And now let me just state some other theorems that are maybe a little less interesting than the main theorem and slightly much more obvious, but still kind of worth mentioning. So the first is a connected sum formula for the boundary connected sum of two four manifolds. The invariant just decomposes the tensor product of the invariant for each of the pieces. And here I've just written it with field coefficients over some field k, just to avoid some Tor terms in the tensor product formula. But in principle, it works over the integers as well. And as a corollary of that connected sum formula, we can also see what happens when we put some non-empty links in the boundary of our four manifold. So remember, that main theorem that we had was only ever considering the empty link in the boundary, right? If you put the empty link in the boundary, really what you're getting is just a four manifold invariant. But you might think, well, that's not very interesting. I want to put some actual links there. So as long as the link that you put in the boundary is like a local link, so a link that lives just inside the three ball in the boundary, then the invariant that you get is the same as the invariant with the empty link, just tensored up with the Khovanov-Rozansky homology of that link. Of course, you could ask, what if we put like really interesting links in the boundary, links that don't just live inside the three ball, links that really only live in this interesting three manifold, the boundary of W. And in that case, I don't really have anything to say about that today. Okay. And finally, people who are interested in four manifold invariants are often most interested in closed four manifolds or closed simply connected four manifolds even. And in particular, our two handle bodies are not closed. Okay, so what can you do to get a closed four manifold? Well, if you could simply attach a four handle to get a closed four manifold, then how does that affect your invariant? Well, it doesn't affect the invariant, and that's not too hard to see. If you just think of this group as something generated by embedded surfaces, well, embedded surfaces can always be pushed off of a four handle, and furthermore, they can be families of embedded surfaces can be pushed off of the four handle. And that fact is enough to conclude that actually the addition of a four handle, or if you think of it as removing a four ball from this closed four manifold, that doesn't affect the invariant at all. Okay, so now we can use this last bit here, this last bullet point, to make a statement about a couple of closed four manifolds by combining it with our results from the previous slide. So, for example, CP2, how do you build CP2 is just the disk bundle over the sphere with Euler number +1, and then attach a four handle to that. And we computed the invariant for the disk bundles over the sphere. And we noticed that in this particular degree, in homological and quantum degree 0, the invariant was 0. Okay, there's a question in the chat. Is there a lag for anyone else, or is it just me? Says Denitsa. Is there a lag? Sorry. I am on Ethernet, so I hope this is not my fault.
Maybe it's just me. Sorry.
Okay, sorry about that. Okay, yeah, just please, shout out if something goes wrong with the audio or video, but yeah, okay. Right, so we get the answer for CP2 by using the result from the disk bundle with an Euler number of +1. And we also then similarly get the answer for CP2 bar, because that's just the disk bundle over the sphere with Euler number -1, adding a four handle to that. But as we saw on the previous slide, in quantum degree 0, that actually had rank 1. Okay, so what we find here is that this invariant distinguishes between CP2 and CP2 bar. So it's actually sensitive to orientation reversal. And this is kind of interesting because it's a very, very small, tiny bit of optimism, a small suggestion that this could have some application maybe to smooth structures. All right, you might be thinking, well, detecting exotic smooth structures, that's many, many miles away from simply detecting orientation reversal, and indeed that's true, but there does seem to be some relation between those two detections, at least in our current understanding of four manifold invariants. So for example, all the interesting four manifold invariants that we do have, like Hagard-Flohr and Seiberg-Witten, that are sensitive to exotic structures, are also highly sensitive to orientation reversal. And conversely, there's these things called unitary TQFTs, or a certain type of four manifold invariant that's insensitive to orientation reversal and also insensitive to smooth structures. So there does seem to be some connection between those two types of sensitivities. So this is like a very small step in the direction of that suggests maybe it's worth looking into how this if this could potentially have any application to exotic structures. And maybe the first the first step in that direction, the next step in that direction would be a calculation of this invariant for S2 times S2 would be very interesting, because that will let us know how what happens to this invariant under kind of stabilizing smooth structures by taking connected sums with S2 times S2s. And in particular, you can use our main theorem to do that, because S2 times S2 is essentially, well, you take a two-handle body associated to a zero-framed hop link and then attach some more handles. But computing the Khovanov-Rozansky homology of cables on the zero-framed hop link, or infinite family of cables on that link, seems a little bit challenging, or coming up with some estimates for what its Khovanov-Rozansky homology could be. But if one is able to do that, then that would be very interesting in seeing how this could be applied to smooth structures.
Can I ask maybe this easy question, but
Yeah.
if you combine the first and the third bullet point, do you get the first bullet point is a boundary connected sum formula.
Right.
You get an honest connected sum formula for closed core manifolds also, same thing?
Yeah, exactly. Yeah, by combining those. Yep, precisely. Right, so yeah, well, what you can see is that basically what I'll say is that if you wanted to use the rank of this invariant, like the rank in a certain bi degree, you want to use that data to distinguish exotic structures. Well, I claim that won't work if you could find, if the invariant for S2 times S2, if you find a bi degree where it has finite but non-zero rank. Okay, if the invariant for S2 has finite but non-zero rank in a certain bi degree, then by this connected sum formula, the rank of the bi degree cannot distinguish between smooth structures due to stabilization. Okay, hopefully it's clear what I mean by that.
So
right.
is this telling us that connected sum with plus CP2 kills the invariant and sum with minus CP2 doesn't, like Seiberg-Witten theory?
That would be very interesting. Unfortunately, not quite, because as you see, it's not quite clear that it kills the invariant, because I'm only telling you what's going on in a very special bi degree. Well, I could tell you all the other quantum degrees are also zero, but I'm only talking about homological degree zero. I don't know if this invariant is still going to be zero in the other homological degrees, but that would be an interesting conjecture to make. Yeah, like Seiberg-Witten, right? Okay. Great. So cool. Those are all the theorems that I really wanted to state. So now let's go back and try to more carefully define the Skein Lasagna module, which I'll go through somewhat quickly because Paul already sort of did this, and then the cabled Khovanov-Rozansky homology, and at the end I'll give a brief sketch of the proof of the theorem. Okay. Yeah. Any other questions before we go into those definitions? Okay, great. So this is a bit of review from Paul's talk, but let me tell you what the Skein Lasagna module is again. So first we need the notion of a lasagna filling. So there's a picture of a lasagna filling of a 4-manifold with a link in its boundary. Here's W is a 4-manifold, the boundary is off to the right. Here's the link L in its boundary. And a lasagna filling basically has 3 pieces of data. There are these input balls inside of W. They're just some 4 balls in the interior. The most kind of complicated piece of information is this framed oriented surface embedded in the 4-manifold, smoothly embedded, and it's such that it has one part of its boundary will be the link in the boundary of W, and the other parts of its boundary will be links in the boundaries of those input balls. Okay, so these interior links like L1 and L2, those are essentially just links in the 3-sphere, all right? And finally, we want to connect this to Khovanov-Rozansky homology. So to do that, we'll label all of the internal links with elements of their Khovanov-Rozansky homology groups. These are these V1 and V2 labels here. Okay, that's a lasagna filling. And in the case when W is the 4-ball, in that particular case, well, in that case, sigma is now it's a surface in the 4-ball. And as Paul explained, we can actually assign to that a Cobordism map on Khovanov-Rozansky homology that goes from the tensor product of the homology of all the internal links to the homology of the external link. Okay, and since we've labeled all the internal links by elements of their Khovanov-Rozansky homologies, we can apply this map to those elements and produce just a single element in the homology of the external link. So this is what I mean by an evaluation of a filling of the four ball. Given a filling of the four ball, we can just evaluate it and just produce a single element in the Khovanov-Rozansky homology of the external link. Okay, so we're going to use that evaluation operation now to define the Skein Lasagna module. All right. So the Skein Lasagna module, it's just a free abelian group generated by all lasagna fillings modulo some relations. So the first is we want it to be multilinear in those input labels. Okay, hopefully it's clear what I mean by that. We're going to mod out by isotopies of basically everything in the picture, of the surface, of the input balls, keeping the link and the boundary fixed, however. That's totally fixed. And finally, the most interesting part of the equivalence comes from this kind of Skein operation, or this local relation that we're going to use that uses the evaluation. So here I've drawn two lasagna fillings, F alpha and F beta. They're different, but they're going to be set equivalent to each other in this group. And the only difference between them is that in F beta, what I've done is inserted some filling F gamma. F gamma is a filling of just the four ball, and I've inserted it into this input ball. This is kind of the operatic structure on these lasagna fillings. And I've done it in such a way that if I were to evaluate this filling F gamma, I'd produce precisely the element V1 in the Khovanov-Rozansky homology of L1. That's the label in F alpha. All right, so this maybe takes a moment to digest, but maybe you also think about it going backwards is kind of how I like to think about it, is start with any lasagna filling, think of F beta, and enclose some region of your filling inside of a four ball, like this dotted line here. Then evaluate away everything in that four ball and erase all that stuff. Now declare that four ball just to be an input ball labeled by the result of your evaluation. The resulting filling that you get by doing that operation is going to be set equivalent to the starting filling in the Skein Lasagna module. All right, so that's the definition. Obviously, it's pretty abstract. It's some huge free abelian group, and mod up by this stuff. It's not really clear how small it becomes. Is this group finite dimensional in each bi-degree? Oh, and I should say that the fillings inherit a bi-degree from Khovanov-Rozansky homology. But is this finite dimensional in each bi-degree? Well, in all the examples I showed you earlier, the calculations that we did, it was, but I conjecture that that's not the case in general, that in general, it's not actually finite rank in each bi-degree. But yeah, I don't have an example to show that yet. So yeah, anyway, it's a lot of things are not understood about the size of this group. All right, so that's the Skein Lasagna module. So now I'd like to go and discuss the cabled Khovanov-Rozansky homology so that we can compare the two. Any questions about the Skein Lasagna module? Okay, in that case, let's continue. So the cabled Khovanov-Rozansky homology, as I mentioned, it's going to be a direct sum of Khovanov-Rozansky homologies of some infinite family of cables on a link, and then we're going to mod out by certain relations. And the first set of relations that we're going to use are going to come from specific cobordisms between those cables. So that's what I want to talk about first. So this is something we can associate to any framed oriented link, but for simplicity from now on, let's just take a knot. So its framing is determined by some integer p, just for simplicity. And to fix the notation, let's say given two non-negative integers, L minus and L plus, I'm going to let K of L minus comma L plus be the link that you get by taking L minus negatively oriented strands parallel to the knot and L plus positively oriented strands parallel to the knot. This is what people usually call a cable of the knot, but also I'm being careful to tell you what orientations I want on the various strands. And that's the use of this notation. So for example, here's a picture when K would just be the +1 framed unknot. This is a picture of K of 1, 1 is the hop link shown in red. And notice one component goes one way, one goes the other way. In blue, I've drawn this ribbon R, just an annulus that twists one full time around the knot. You can think of this as the ribbon that defines the framing on the knot. But the reason I've shown it is because one interesting thing is that the boundary of this ribbon is K of 1, 1. Okay, so for example, if I'd done K of like 2, 0, that's the same cable. It would still be the hop link, but since both components would go in the same direction, it wouldn't be the boundary of this ribbon as an oriented manifold. That's why I kind of like this K of 1, 1 a little bit better than some other orientation on this Hopf link. Okay, now we're going to use this ribbon to build the cobordism that I want. So the cobordism is going to go from K of L minus comma L plus to L minus plus 1 comma L plus plus 1. In other words, I'm going to add an extra strand in both directions. Okay, and the cobordism is going to be just a cylinder on the starting cable, just the identity cobordism. But now I want to add these 2 extra strands. So to do that, I introduce a copy of this ribbon shown in blue. All right, so let's call that cobordism Z. That's going to be the cobordism, the important cobordism that we're going to be using. And I'm also going to need a slight variation on it, which is just the same cobordism, but we're going to decorate that ribbon piece with a dot. So this is just, you know, that in the sense of like the Barneton cobordism category, where we can decorate surfaces by dots and associate maps to on Khovanov homology to those. And from now on, I'm only going to be focusing on the case when capital N equals 2, just the case of Khovanov homology, not the more general Khovanov-Rozansky homology. Just for simplicity, everything can be done for general N as well. But yeah, just for the sake of simplicity, you know, for example, for general N, I would need to consider having up to N minus 1 dots on these on this cobordism here. So, but just to keep things easy. Okay, so we're going to use this cobordism in defining the cabled homology. But we need one more ingredient to define the cabled homology, which is a certain Braid group action. It's actually going to be a symmetric group action. I'll explain that later, but for the sake of this talk, I'll call it a Braid group action. So consider the Braid group on L minus plus L plus strands. Okay, that's like the total number of strands in my cable. And now consider the subgroup that is only going to permute the first L minus and the last L plus strands among themselves. What I mean by that is if you think of the natural map from the Braid group to the symmetric group, right? Consider basically the pre-image of the product of 2 symmetric groups. So the product SL minus times SL plus. That's the group I'm considering. So the first L minus and last L plus, they can kind of intertwine amongst each other as long as they end up kind of still in their own separate groups, right? So the associated permutation to the braid doesn't mix the first L minus and last L plus. That's because I want to keep the strands that I'm permuting oriented the same way. So this particular group, the subgroup of the braid group, acts by symmetries on the link on the cable in the following way. Here's a kind of a picture. Here's a cross section of a neighborhood of the knot. So think of the neighborhood of a knot as a copy of D2 times S1. Here's the D2 factor, and the S1 goes kind of around this way, but I've just sort of sliced it somewhere. So here are a few components of my cable. 2 of them are coming towards us, 2 are going away. They intersect the disk in a few points. And now if you think of the braid group as the mapping class group of a marked disk, the braid group acts by automorphisms on that disk, moving those points around, right? And then if you act by the identity on the S1 factor, it'll do the same thing, just moving all the components of the link around. And so in that way, we get some symmetry of this cable. And whenever you have a symmetry of a link, you can view that symmetry as a cobordism in 4-dimensional space, a self-cobordism, and thereby obtain an action on the Khovanov-Rozansky homology. So we get this action beta is an action of this subgroup of the braid group on the Khovanov-Rozansky homology of this cable. And since writing this paper and having given this talk a few times, I've been informed that actually this action factors through the symmetric group. At least in the case when capital N equals 2, it's clear to me that it now factors through the product of the 2 symmetric groups, SL minus times SL plus. This follows from work of Grigsby, Licata, Verley. They show that this is actually the case. So if you'd like, you can just think of this as a symmetric group action or action of the product of 2 symmetric groups. But for the sake of this talk, I'll just call it a braid group action. Hopefully in some revision to this paper, we maybe make some kind of comment on how this actually factors through the symmetric group. Okay, so this is the last little bit of information that I need to finally define the cabled Khovanov-Rozansky homology. So let's do that. Okay, so what is it? So first of all, we need this extra parameter alpha, which in this case will just be an integer. If you remember in the main theorem, on the Skein Lasagna side of things, this alpha is what will correspond to the second homology class of the surfaces we're considering. On this side of the story, in the cabled homology, it's just some extra parameter that's going to enter into the definition somehow. It's not terribly important. And in general, it could be in z to the number of components in the link. But for now, we're just only focusing on the case of a knot just for simplicity. So it's just some integer. So, okay, here's the start of the definition. Again, we're only considering capital N equals 2. That's why there's a subscript 2 here. Again, just for simplicity. And that's why I'm writing just Khovanov homology, not Khovanov-Rozansky. So essentially, this is just the direct sum of the Khovanov homology groups of an infinite family of cables. So as R increases, you can see that we add an extra strand in both directions to our cable. Okay. And these parameters alpha minus and alpha plus are just some negative, they're the negative and positive parts of alpha, just they depend on just on this parameter alpha. This term embraces is just some shift in the quantum degree, which I won't really worry about now. But the interesting part are the relations that we're gonna mod out by. So what are those? So the first is this braid group action. We're gonna mod out by the braid group action. Set everything equivalent to its image under the braid group. Okay. Second, we're going to use that Cobordism map Z that I discussed. That was the Cobordism that it adds 2 components to our cable, one in each direction, right? It's this cylinder together with this ribbon, and we're going to mod out by the image of that Cobordism. So this Z, if you think of it in this direct sum, the Z Cobordism map goes from like the rth part of this direct sum to the R plus first summand in the direct sum. Okay, adding an extra component in both directions. All right, so we're going to mod out by that map. And there's also that Cobordism Z dot, same thing, just with a dot on it. And we're going to form some kind of a co-limit with respect to this map. Set everything equivalent to its image under the Cobordism map for Z dot. Okay, if we wanted to do higher n, we'd have kind of analogous relations to this first to the Z relation for the extra for the other numbers of dots we could have, but let's just only think about n equals 2 now. All right, so
yeah. Quick question. This is Melissa. Was the Z map the ribbon bound by a hop link or just 2 parallel circles? Like, does it have framing 0 or?
Right. So let me just go back to the picture real quick. Okay. Yeah. So here's the Cobordism Z, and so you take the starting cable, just do a cylinder on it to just go to itself, the identity Cobordism. But to add these 2 extra new components, what I do is I add a copy of the ribbon. This is the ribbon that. So yeah, take the knot K, and it has some ribbon that goes around it defining its framing. It's that ribbon.
Okay.
Right, and so its boundary will add. So in the case, yeah. So it's not just 2 extra circles that are just giving you 2 unknots. It's in the case of the +1 framed unknot, for example, it would be a ribbon that gives the hop link. It's not always that. I mean, the knot could be some complicated thing with some crazy framing. Yeah, that's what it is. It's that ribbon. So that's how. Right, or you think about it this way. Think of a cable. What is a cable? It's you take this ribbon, and then you draw a bunch of parallel lines on that ribbon, right? So what we want to do is just draw 2 more parallel lines on that ribbon to add 2 components, if that makes sense. I don't know.
Yes, that's clear. Thank you.
Cool. Okay, excellent. So yeah, that's those are all the definitions that I needed to go through. So now hopefully we have some kind of better understanding of the objects that appear in that main theorem. So now I'd like to get into the sketch of the proof of the main theorem. So are there any more questions about the these definitions and things?
I'm a bit confused about the role of this alpha. Isn't that what's going to be actually given by the framing, or?
No, the alpha is so. Right. Okay. Good question. Yes. In this cabled homology, it's really just an extra parameter that it essentially it tells you how many components you start with, right? So let's just, we're only going to focus on alpha equals 0 pretty soon because that'll be easier. If alpha were 0, then the cables I'm considering are cables where there are one component in both directions, two components in both directions, so on and so forth, even numbers of components every time. If alpha were, let's say, just +1, then we'd start with just one component in the positive direction, and then the next, when R increases, we'd have two components positive, one component negative,
I see.
so on and so forth. And it's supposed to correspond, we'll see in the proof how this corresponds to the homology class, the relative homology class of the surface on the other side. If you think about, well, I can give kind of just a spoiler on that, is you think about attaching a disk along this framed link in the two-handle body, the homology class of that, or a bunch of disks, the relative homology class of that disk is what alpha will be, right? If you had a, right, so yeah, okay, well, we'll see that in the proof.
Thanks.
Yeah. Okay. Great. Okay, if there are no further questions, then I will sketch the proof of the main theorem. So let me just remind you what the theorem says is the following thing. It's just this isomorphism between the cabled Khovanov-Rozansky homology of a framed link K and the Skein Lasagna module of the two-handle body associated to that framed link. And this is, again, the Skein Lasagna module just with the empty link in the boundary. All right. And we're going to immediately make some simplifying assumptions just to keep the notation not too messy. We're going to take K just to be a knot rather than a link. We're going to just do capital N equals 2, the case of Khovanov homology, rather than the more general Khovanov-Rozansky theory. And we're going to set that parameter alpha equaling 0, just for simplicity. So we're really only considering null homologous surfaces. But as we'll see, we can still have plenty of interesting surfaces in our four manifold, as long as they kind of come in canceling pairs in homology. So it's not a huge restriction. That's kind of the gist of the argument can all be understood just from this simple case. All right. So what do we have to do? So the first thing I want to do is define a map phi tilde that's going to go from the direct sum of the Khovanov homologies of the cables, this infinite family of cables, a surjection to the Skein Lasagna module, right? So first I want to define the surjection, and then we'll try to analyze the kernel and show that it factors through the cabled Khovanov homology, and that it then provides an isomorphism. Remember, the cabled Khovanov homology is just some quotient of this object on the left. Okay, this big direct sum gets quotiented to provide the cabled Khovanov homology. So we're going to start just with the direct sum and then try to analyze this kernel. All right, so how are we going to define this map? Well, pick your favorite element V in one of these Khovanov homology groups, and I'm going to try to define a lasagna filling, which I'll call F sub V, associated to that element. So how do we do this? Well, here's a picture of the four manifold on the two-handle body on the right here. The bottom half of this picture is the zero handle, top half is the two handle. In red, I've drawn a link in the boundary, the link, the cable. In this case, I guess it's K of 2, 1. But since we're setting alpha equal to 0, actually all the cables we're considering will have the same number of components in both directions. So this isn't quite the picture we're considering. Maybe if you added an extra component going to the left, it'd be K 2, 2, and that's more like what we're thinking about here. So that this red thing appears in the boundary of the zero handle. And in blue, inside the zero handle, these blue things are supposed to be disks in the two handle, core parallel disks. Okay, I'll say a little bit more about those in a moment. So now let's try to construct a lasagna filling. So we need three things, right? We need an input ball, first of all. So let's just take the zero handle to be our input ball. We need to decorate that with a link. We'll just use K of R, R, and label that link with an element of its Khovanov homology. In this case, just the element V in that we've chosen in the Khovanov homology of K of R. Okay, and finally, we need this surface, a surface whose boundary is precisely that cable, K of R, R, inside the four manifold. And so what we're going to do for the surface is to take these core parallel disks. So what do I mean by that? Well, if you think of the core of the two handle is some disk, and based on the way we've attached it, right? The idea of attaching a two handle along a framed link means that the core of the two handle, that disk, its boundary will be the framed link in the 3-sphere, okay? And then if I take a bunch of parallel copies of that disk, the boundary of several parallel copies of this core disk will be a bunch of parallel copies of my framed link, my framed knot in this case. In other words, just a cable on that knot. So what I'm going to do is take 2R such disks. So the boundary will be this cable of my knot with 2R components. And there'll either be, I'll call them C lower j. J goes from 1 to R. And there'll be some of them, half of them labeled plus, half of them labeled minus. So R will be plus, R will be minus. That just refers to the orientation on the disk. I'm going to orient half of them one way, half the other way, so that their boundary as an oriented manifold gives me K of RR, which remember K of RR has half of its components, there are 2R components in the link, but half of them go one way, half go the other way. And then notice then if we assign the orientations that way, then this surface has trivial homology class relative the 0 handle. Okay, right? If you think of the generators of H2 of this two handle body, or think of the, right, they're precisely these. A generator of the homology is just a kind of a sphere that wraps around the attaching where we've attached the 2 handle. So relative to the 0 handle, one of these disks oriented positively would generate the Z in the homology. So by taking 2R disks, half one way and half the other way, we get overall homology class 0. Okay, if this alpha were some other number here, we'd have to have kind of an odd number or an unbalanced number of disks with the other orientations, but not so different. Cool. So that's the lasagna filling I'm going to assign to this element V. So we're going to set phi tilde of V to be just the class of that lasagna filling in the Skein Lasagna module. All right. Now, but you might wonder, I haven't said, why is this surjective? So I mean, a priori, it doesn't seem very surjective because the Skein Lasagna module, remember, is something generated by like all lasagna fillings. So all sorts of crazy embedded surfaces contribute to the Skein Lasagna module. And here I'm only considering some rather boring surfaces, just these core parallel disks. However, it is in fact surjective. So the picture you have to think about is take any arbitrary surface in this 4 manifold. Okay. What you can do with that surface is by an isotopy, you can push the entire surface down into the 0 handle, except for maybe a few core parallel disks living in the 2 handle. Depending upon the geometric intersection number of your surface with the co-core to this 2 handle, you'll be left with some number of disks in the 2 handle, but the rest of the surface can get pushed into the 0 handle, right? So all of the interesting topology, you can push it down into the 0 handle. And once you've done that, once you've pushed all the interesting stuff in your surface into the 0 handle, well, now that all will live inside of a 4-ball. So we can just evaluate away all that stuff and produce an equivalent lasagna filling that looks exactly like this. Okay, so that's kind of the argument for why it's surjective. All right, so now what I want to do is analyze the kernel of this map. The first thing I want to do is see why it factors through the cabled Khovanov homology, and why does it preserve the relations in the cabled homology. So the first thing to think about is this braid group action. Well, if you think about it, all the braid group's really going to be doing is permuting these disks. Okay, so another way of saying it is if I act by this braid group and then apply the map phi tilde, how is that different from applying the map phi tilde? Well, the braid group's just kind of moving the link components around. So if I do that first and then apply the map phi tilde, I'll get essentially the same lasagna filling, just some of those disks will have been moved around by some isotopy. Okay, so it's a different filling, but they're isotopic, just the disks have somehow been permuted in some way. So ultimately it's equivalent in the Skein Lasagna module. So that's kind of hopefully not too difficult to see. The more interesting thing is what's going on with these Z and Z dot Cobordism maps. So to understand that, we have to look at this other filling, E sub V, I'll call it. So what is this filling? Well, on the left here, we have the 0 handle, and on the right is the 2 handle, just in the white space here. And B prime is just a slightly smaller ball than the 0 handle. That'll be my input ball for this filling, labeled by one of these cables, K of R comma R, and with some element V in its Khovanov homology, that's the V here. And what's the surface? Well, in between the input ball B prime and the zero handle B. In that region, I'm going to introduce a copy of that cobordism Z. So that'll go to K of R plus 1 comma R plus 1, adding 2 components in each direction. And it goes by a cylinder together with that ribbon. Here the ribbon is shown just kind of as an annulus to add those 2 extra components. And then now we're at the interface of the 0 and 2 handle. And now we're going to add those core parallel disks, just capping off all the components. Okay, this is some new filling I'm defining. And it doesn't exactly look like something in the image of phi tilde because it's got all this weird stuff happening inside the 0 handle. So I want to make this look like something in the image of phi tilde. And so I'm going to have to do the process I just explained that proves the surge activity, which is just to make it look like something in the image of phi tilde, I have to evaluate away everything in the 0 handle. And that's precisely this cobordism map, this cobordism Z. So what happens is the evaluation will just be applying the cobordism associated to Z, applying that to this element V, and that produces some element in the Khovanov homology of KR plus 1 R plus 1. And then you'll erase everything in the 0 handle, and then you'll have something that looks exactly like the fillings I described on the previous slide, something with just a few core parallel disks in the 2 handle labeled by some element. The element it'll be labeled by is the Khovanov of Z applied to V. So this filling, E sub V, is actually equivalent to one of the fillings I just defined, F sub something, F sub Khovanov of Z applied to V. And you can do the same thing with the dotted cobordism. If we have a dot here, I'll call that cobordism EV dot, and that's equivalent to Khovanov of Z dot applied to V, F sub that. Okay, why does this matter? Why is this relevant to showing this factors through the cabled homology? Well, what we have to do is look at just this part of the picture here. This part of the picture, this is where I added that annulus, that ribbon, to add 2 new components to the link. And then I capped off both those components with spheres in the 2 handle. So ultimately, that piece there is just a copy of S2. And in fact, if you think about it, you can actually isotope that sphere off of the 2 handle entirely. This will just be some free floating sphere. You can just think of it living anywhere you like, maybe in the 0 handle. But what that means is that we can apply the evaluation map just to that sphere and think about what is the map Khovanov homology associates to a sphere. Well, it always associates 0. In other words, anytime you have a disjoint sphere somewhere in your lasagna filling, you can evaluate that producing 0, and the entire filling gets killed. So this entire filling is actually equivalent to 0. Similarly, if you had a dotted sphere, the map associated to a dotted sphere on Khovanov homology is 1. So the identity map. So anytime you have a dotted sphere, you can just erase it from your lasagna filling by an evaluation. So now we see precisely the relations that appear in the cabled Khovanov homology. The idea that the image of the Z cobordism map is equivalent to 0, and the image of V under the Z dot cobordism is equivalent to V. All right, so that's why it factors through, this map phi tilde factors through the cabled Khovanov homology. All right, now I think I have maybe another minute or two. Hopefully I can explain just briefly why this map has an inverse. So since this map factors through the cabled homology, we'll define phi to be that map, the factorization. And I want to show that it has an inverse map. All right, this is maybe a little bit harder to see just in a short talk like this, but I'll just briefly explain how it kind of works. So roughly what we want to do is, given a class of some lasagna filling F, its class is a class of F in the Skein Lasagna module. I can view it, and in the image of phi tilde, I can say it's phi tilde of some element V in one of those Khovanov homology groups. So I'd like to set phi inverse of this class to be the class of V in the cabled homology. But to define this element V, that requires perhaps doing some isotopy or some evaluations on that lasagna filling F. And there are many possible ways of doing those isotopies and evaluations. And depending on how I do it, I'll get a different answer for V. And I want to say that all those different answers for V are actually equivalent in the cabled homology. So we have to consider those different choices of isotopies. So here's the picture. Roughly, what you want to think about is the number or the intersection points of the surface in your filling with the co-core, shown in green here. If, as you're doing your isotopy, the number of intersection points with the co-core doesn't change, that's not what's shown in this picture. If the number of points stays the same, all that's happening then is the points in the co-core disk are just being moved around somehow, permuted in some way. And that permutation is recorded by some element of the Braid group. So depending on whether you define V before or after the isotopy, those two choices are related by this braid group action, and thus will be equivalent in the cabled homology. Maybe a little bit more interesting is what happens when under this isotopy you add or cancel two intersection points, like what's shown in this picture. And that's where the Cobordism map for Z comes into play. So if you think about think about this purple region here, this purple point, if you were to cut the surface at that point, so this is actually disjoint, if this were a disjoint sphere over to the left, and this were just closed off here, then if we use the picture on the left to define our element V, we'd evaluate everything in the zero handle, but this disjoint sphere would kill it. So it'd be zero if we use the picture on the left. The picture on the right, however, if this surface were kind of cut at that purple region, then you wouldn't get zero, but what you'd get is something in the image of the Cobordism for Z, because the region between this dotted line and this boldface line is the Z Cobordism. Okay, so again, it'd be equivalent in the cabled Khovanov homology. And similarly, if you just ignored this purple thing and it was actually connected, the surface were a connected surface here, then what you'd get from doing it on the right would be the Z dot Cobordism, which appears in this region between the dotted and boldface line, applied to whatever the element you got from doing the evaluation using the left. Okay, so that's roughly how it goes. Maybe it's a little bit kind of difficult to see just in a quick talk like this, but hopefully it gives you some flavor of the argument. All right, well, that's all I had to tell you today, so thank you very much for listening.
Great, so let's thank Ikshu for his great talk. All right, are there any questions?
I suppose it's too early to speculate on whether the parity of B plus makes any difference. Or...
The parity of B plus. Oh, yes. Okay. Yeah, I don't know. Yeah, good question. Unfortunately, that we have very little computational data to conjecture about such things quite yet. But yeah, that's an interesting thing. Right, because we have all we really have, I guess, in this line is between S4 and CP2 and I guess CP2 bar, but that's kind of it. Yeah. So yeah. Right.
So can I just ask, how far did you get with the computations regarding somehow the cabled Hopf length, the zero cabled Hopf length, the thing that somehow gets you towards S2 times S2?
Oh yeah, not very far. I mean, well, the goal. Well, I started with kind of the conjecture that it would be infinite rank in some sense, and I tried to prove some bounds. So you can try. That's maybe the kind of the best. I think the easiest avenue of attack is to try to come up with some bounds for its rank. But yeah, it is a little bit complicated. I mean, okay, no. What's clear is coming up with some bounds for the ranks of the Khovanov homologies of those groups and showing how quickly they grow. That's reasonable, but the Cobordism maps that appear and kind of getting some control over how those relations play is a lot trickier, I think. Yeah, so right. So let's say if you just took the cabled homology, mod the symmetric group action, that you can come up with some bounds on kind of how big that grows as you add components, sort of reasonably. But how much those Cobordism maps kill is, yeah, that's a little bit trickier.
Is there a way to compute this like handle by handle? I mean, if you already have the trivial bundle over S2, can you just add another handle?
Right. Good question. Yeah. So this whole main theorem was just about 2-handle addition, and like I said, 4-handle addition is trivial, doesn't affect anything. So what about 1 and 3 handles? Okay. Well, it's not so hard to see that adding a 3-handle will just make the invariant smaller. We'll quotient by something, but it's not totally clear what that is, right? So, for example, you could add like in the case of S2 times D2, you can add a 0-frame 2-handle and then add a canceling 3-handle to get back down to S4 and kill a bunch of stuff. So potentially adding a 3 handle kills quite a lot, as we saw the invariant for just S2 times D2 is, it has a kind of a rank 1 and it could have rank 1 in all negative even quantum degrees, for example, and then adding a 3 handle would kill all of that. So how much does adding a 3 handle kill? Not clear to me. Adding a 1 handle seems, you'd think that would make that invariant bigger. And in fact, yeah, I think it'll make it a lot bigger, but that's a lot more complicated. I think there's some work, I don't know, Paul, if you've been thinking about this, or I'm not sure, but maybe you could comment on it. But if you think about the issue with a 1 handle, right, is there's a lot more kind of crazy surfaces that could happen that are hard to maybe simplify. Like once you had a 1 handle, then you have like a naught times that S1 factor, and you come up with tons of interesting surfaces that could potentially contribute. So it seems like it would be a lot larger, and I don't really know how to get a good control over that situation. Yeah. So
I have sort of related question, also just philosophical, but so if you were to understand 3 handles, I often think like people say in 4 manifolds, you don't need to think about 3 manifolds because of Laudenbach and Poincaré, but that's sort of a lie because you need to know how they're glued on in, if you have a 4 manifold. So supposing one could do the computations to understand what happens with 3 manifolds, with 3 handles, would it somehow allow you to compute invariance for closed manifolds without actually recognizing that the boundary 3, without you have to know what the diffeomorphism is between your boundary 3 manifold and connect some of S1 cross S2s in order to glue on a 3 handles, right?
Right, yeah.
So
yeah.
The question I'm trying to get at is, would it be important is this the kind of invariant where in principle one would need to understand that diffeomorphism of the surgered 3 manifold to connect some of S1 cross S2s in order to continue the computation? Or would it be something where you could just say, oh, Laudenbach Poincaré says there is a diffeomorphism, so it doesn't matter?
Good question. No, I think you really would have to understand the diffeomorphism specifically for this kind of thing, because, well, okay. I mean, okay, intuitively, right? Depending on what diffeomorphism ends up being used for that gluing, there could potentially be like different knots. Like, so take some knot in S2 in one of your S1 times S2 factors, or these connect sum factors, right? Depending on what diffeomorphism you use to glue the 3 handle onto that boundary S1 times S2, there could be different knots in S1 times S2 that are bounded by a disk in the 3 handle or not, if my understanding is correct. And depending on that, this invariant would be different, because if I had some knot in S1 times S2 and it gets bounded by a disk in this glued on 3 handle, then that allows me to produce some certain type of lasagna filling. And if in a different diffeomorphism it didn't get bounded by a disk, then I would have I wouldn't have access to that type of lasagna filling. Maybe, if that makes sense. So you can think of it as, yeah, maybe you're getting generated by all these Khovanov homology groups of all of these links inside of S1 times S2, but then maybe we're killing lots of things that are getting disks attached onto them. So depending on which things get disks attached, you would get kind of different answers, perhaps.
The disks you could always pull down off of the 3 handle.
Okay, so then there's no, okay, then right, okay, so the issue with 3, I mean, right, this, yeah, of course, the disk, so surfaces can always be pushed off of the 3 handle, certainly, but the issue is that since the Skein relations, I mean, involves isotopies of these surfaces, right? So the families of the disks might not be able to push them off into families. So there might be different isotopies that exist in a certain 3 handle attachment versus another one. So those might add different relations to the Skein module in one case versus the other. That makes sense. Yeah, that's the issue. Yeah. Unlike for a 4 handle, you can not only push off all the disks, but you can also push them off in families. So it really doesn't affect anything.
I think I might have misunderstood something. Can you go back to page 13? It's like where you were capping off Yeah. Okay, here's maybe a dumb question. Let's say I have just a 4-ball with a like 0 frame 2 handle attached, and I think about the core of my 2 handle as being glued to a disc that's inside my 0 handle.
Yeah.
Does that evaluate to 0?
Evaluate 0. No. So what would be happening in this? Like you're looking at maybe this part of the picture with the sphere, right?
Yeah, I was
Yeah.
confused how
So-
you were able to push it into the
right. So
not
what it would be in that case would just be there are two guys here, and I've kind of drawn them side by side, but really they should be think of them as more nested. But I guess for the 0 frame case, it doesn't really matter. But yeah, so what you'd have, think if you have an unlink, right? Just a 2 component unlink in the boundary of the sphere, and then that 2 component unlink bounds this ribbon, which is just trivial. So there's just a tube, just a cylinder inside of the 4-ball, and then both of those, both of the boundary components of that tube get discs inside the 2 handle. Okay, but you think of the discs. I mean, they're drawn here parallel, but they're really kind of more like, I don't know, think of them as nested somehow, right? So there's the isotopy that pushes it off. It's kind of a it pushes them off. You know, like yeah.
So those discs that you're capping off with aren't like the core of the 2 handle or isotopic core. They're
they're parallel. Yeah, they're core parallel discs, right? So
okay.
so they're
maybe.
2 core. Yeah, sorry. They're, I mean, think about. Okay, let me try to this more carefully.
No, I think I'm probably just not imagining in the correct number of dimensions. Actually,
Just think about a disc cross I inside of the 2 handle when the 2 boundary components are your parallel 2 discs. And then it's kind of easy to see you can push the whole thing off of the 2 handle.
Yeah, exactly what's happening.
okay.
Yeah, sorry. This picture is a little bit misleading because I've shown everything kind of side by side to each other for simplicity, but maybe it's, in my mind, I usually think of them like in the previous page, I had kind of them, I've drawn them kind of nested here. So maybe this is a little bit better of a picture to look at. If you just think of there are 2 blue guys, one in, maybe at the top 2, one in one direction, one in the other direction. And then this, there'd be in between the 2 red dots, it would be kind of filled in with that would be the ribbon. And then, yeah, you would just kind of push this guy all the way around there. Like, yeah, okay, maybe
Yes. I see the extra space for pushing it down now.
Yeah.
Thank you.
Yeah, it's not so intuitive from this kind of a picture. Yeah.
All right, so I'm going to cut off the questions here. Well, if you have some more, you can ask him at T. And let's thank Ikshu again for his great talk.